just take you over it. It's more of a practical application of Bayesian statistics, because I'm nervous that the math side people have worn t-shirts today. It's statistics lecture, so I'm worried. But I think it'll be a nice little tour through why you want to use something like Bayesian statistics through Pulsar Timing, and the beginning in how we tend to do this, which we're going to explore more tomorrow. We actually do some noise modeling and noise sampling stuff, which will be a lot of fun. So a bit about getting started off. This is my pictures of me looking very cocky, but my name is Matt. I am a postdoc at Swinburne, but don't actually have a doctorate thing yet. I spent my thesis about 3 weeks ago, but don't tell anyone, it's a long job. And I'm really, really interested in noise modeling, and in particular, gravitational waves. So I love the aspect of pulsar timing arrays, which lets you search for those low frequency gravitational waves, and also all the noise that kind of gets mixed up in the middle of it. Personally, I really like doing a lot of hobbies like hiking, traveling, snowboarding, surfing, I don't use it, but all very bad. It makes it a lot more interesting to me because I get to keep learning, and hopefully, because I don't seem to be improving, I get to keep learning my entire life, which is great. But yeah, to begin, just a little bit of frequentist versus Bayesian statistics and how I kind of do it. So we have these two very broad camps, which I'm now going to separate all statistics on Earth into. And I'm call them frequentist and Bayesian, because that's what their names are. The frequentist side of things is the likelihood of observing some likelihood of observing some signal in the data given some model of the town. But the Bayesian side of things is the likelihood of observing a model given the data under some kind of hypothesis which you have a prior belief about. And that prior belief is constrained by these frames, and hopefully they're informative. And so you can do things like this, represented on the cartoon over there, which is, if you think you have a measurement device, and it tells you that there's a very good chance in the frequency world that the sun has exploded. You can use your hopefully informative priors to tell yourself that the sun hasn't actually exploded, and you can get yourself in place, which is the most important thing in all statistics. But while they both can give very reasonable results, in pulsar timing we really want to use the more Bayesian version of these things. And the reason for that is better explained this. In the frequency landscape, the signal is fixed, the data is considered random. In pulsar timing, we do not think that the data is random. The data comes exactly when it's meant to come. We have no idea what the signals are in this data, and so they can be inferred. And so we need to search through lots of different possible models of these signals and compare them all iteratively, very carefully, so that we can build what the actual correct model for the data is, the model that the data infers. And we do this through Bayesian statistics and what we call Bayesian inference, which is comparing all these statistical models. And I'm going to pass quickly over to Daniel to begin the background statistics.
Okay, thanks. Yeah, so before we talk about Bayes' theorem, where we probability distributions and use Bayes' theorem to get probability distributions for our parameters, we first want to get used to this idea of thinking about our measurements as probability density functions. So measurements always have uncertainties. When we want to measure GOAs in the last exercise and in the last exercise, we have these error bars. So these standard errors can be turned into some belief about the probability of observing some model given a beta. So in this example here, I'm measuring my book, Practical Statistics for Astronomers, and my measurement on this scale is 608 grams. So whatever the true value of this book is, it's been rounded to 608 grams, and so we say that the precision of this measurement is 1 gram. If I put it on a better scale, then I get 608.5. And so this 0.5 is now the precision level, so it's given me a number to the nearest 0.1 gram. So I can look at these measurements and I can say, okay, given these, what's the probability that the true value lies in some range? And this is what we might see. So probability density functions are plots like this, where the total area under this curve is 1. But basically this means you guaranteed to have a result somewhere. Some number is going to be displayed. So yeah, probability is 1. So with a less precise scale here, that's rounded to the nearest gram, what we can see is that any between 607.5 and 608.5 is going to be rounded and displayed as 608. And so you can see that the probability density function for this measurement is something like this. And for the more precise scale, any mass measurement within this range is going to be displayed as 608.5, and so we've got a larger probability density function here for that more precise scale. Okay, but in reality, we rarely see probability density functions that are these rectangle shapes. They're rarely a good description of data because there's lots of things that can go wrong. Maybe there's just random errors in the scale. Maybe there's a bit of dust on the book and that's shifting this distribution. And so in real world applications, we quite often see a distribution like this, which is the normal or Gaussian distribution. So in the next few slides, we're going to be talking about using this Gaussian distribution to describe the likelihood of our data. But really, it's not that important. You can use the likelihood, any likelihood function you like. Okay, so this normal distribution is given by this equation. Sigma here is the standard error in the measurement. So this is like TO170 that we had before. X is the sample measurement of the random variable. So for example, the book mass. Mu is the mean, so we make multiple measurements. We do have a notebook that in the virtual machine, which is located here, if you want to have a play around with this. If you remember yesterday, I showed there was a demonstration of moving a template over some pulse profile. That's also located in here if you wanted to play with it, but we won't go through that now. Okay, so yeah, this is that same demonstration that I showed before. So one way to fit a model to data is to just do a regression analysis, which is like least squares fitting. So what we do here is we take the difference between the data, which are these blue measurements, and the model, which is orange. We subtract the two and we get residuals that look like this. So if we square those residuals and sum them up, and we divide by this sigma squared, so we basically weighting them so that smaller error bars contribute more to this factor, we get this high squared value. And at least squares fitting, like we did in 2.2, we're trying to just minimize this number, and then that's the best model description here. But now we want to try and think about these measurements in error bars instead as probability density functions. So if we use something like the Gaussian likelihood, the function for the Gaussian, you can see that the probability of your data given some model is proportional to e to the minus half chi-squared. So this chi-squared is easily related in this Gaussian likelihood. So in this plot up here, I'm showing. So when we're fitting this pulse profile model, we're fitting two parameters: the amplitude of this and the phase shift, and we're trying to optimize those two parameters. So if we look at the grid of this chi-squared value as a function of the amplitude here and the phase shift, we see this kind of distribution, and in least squares fitting, we're just trying to find the minimum here. So because this probability is proportional to e to the minus chi-squared, finding the minimum here is equivalent to finding the maximum likelihood value here. Okay, so, sorry, I'm going to do that. So, now these measurements and the error bars are over here. So, we're thinking about these as now normal distributions. And we're trying to find the orange curve that minimizes the product of all of the probabilities, where this orange curve slices all of these normal distributions. And that is the maximum likelihood. So that gives us this middle part here, the likelihood of observing the data given some model parameters. So the notation here is different. This is what I call P of X and previous slide. So in Bayes' theorem, we have a few more ingredients. We have our prior understanding posterior probability distribution, which is the probability of our parameters given the oscillations that we make. So this is the equation that we used to do it. This is Bayes' theorem. So this probability of the model parameters given the data, that's the posterior distribution. Our likelihood, where we use the Gaussian likelihood a few slides ago, that's given here. This is our prior. And this Z is just a normalization factor. This is just the integral over all of the parameters that describes this numerator here. So we can do model comparison using these normalization factors, depending on how we're doing the Bayesian inference. We sometimes get this number out, and we sometimes just don't worry about it and consider it arbitrary. But if we do have that number, we can actually use it to compare different models. So if we go back to the previous slide again, this evidence factor is the total, basically the total area under the curve of your likelihood times your prior. So you can imagine that if you have a better model, the model is more likely, and so you've got more volume or more area under that curve. And so this evidence number is going to be higher. So we define this thing called the Bayes factor, which is the ratio of these evidences. And there's various ways to interpret this Bayes factor. Matt might be talking about some of those. But yeah, we can take the ratio of model evidences, and that's how we can find the best model description for the data.
So in the Pulsar Timing particular PTA world, how we generally sort of tend to do this is through quantity space sampling techniques, which are algorithms that have been created in order to create that posterior distribution. So the two ones that are definitely the most common that I've encountered at least are what you call micro-chain Monte Carlo algorithms and nested sampling algorithms or techniques. Both are very, very good for different reasons. Markov chain Monte Carlos enable this direct model comparison, that you can sort of transdimensionally sample for different models that you're sort of comparing to each other, and you get a direct literal Bayes factor out of that way, such that you don't actually have to compute any evidence or anything like that. They're also very fast, and they are what we call sort of trivially parallelizable. So if you have something like a cluster computer, like a supercomputer or something, which has tons and tons of cores, what you can do is you can just separate these Monte Carlo chains into Monte Carlo chains into tons and tons of independent jobs, and then staple them back together at the end. So it's very, very easy to make this a very, very fast process, which is important given that sometimes when you're looking at a full PTA with 90-odd pulsars and potentially hundreds of different models that you could be described with, that can take weeks of computational effort to get done. So anything that can be made faster in this sense is very important. This can be made faster in this way. However, it has some downsides. It's very difficult for an algorithm such as this to work on multimodal distributions, or very efficiently on multimodal distributions, often which we see in Pulsar Timing range, where it's not necessarily clear which parameter best describes the model in the product space. And so that's where nested sampling comes in. Nested sampling is a little bit better at constraining this kind of stuff. It isn't as parallelizable. It's a bit harder to split amongst the cluster computers if you're trying to do something like that. But it has this great advantage that protects against any unsampled prior space. And so you can be pretty confident that you're actually getting the true answer back, and it's not just stuck at a point in that Monte Carlo chain you might get otherwise. But this is so this is supposed to be what people term the PTA analysis pipeline, which is to chuck in your prior and your likelihood into this MCMC machine, and you get that posterior and your evidence which describe what best describes your data, the model that best describes your data. And so we're really just focusing on MCMC in this workshop tomorrow. When we have a crack at it, we're just going to be using MCMC. If you are interested down the line and trying to get nested sampling to work with this kind of stuff, I've spent too much time doing that, and I can definitely help you. But it's a lot easier to sort of visualize this, so we're going to take a really quick break from the slideshow into this lovely little MCMC visualizer. You can all kind of see what I'm talking about. So, click on that. Yeah, okay. So this is basically the algorithm exploring this 3 modal, just 3 modes on this distribution. So you see those circles there, that's where the model was meant to select, and this is sort of the MCMC trying to find a good description of those little nodes there. So what it has here is really just the main thing that's good at controlling it is a sort of like proposal value here. I'm going to just bring this down a little bit more so it's a bit faster. And eventually you should be able to see that it's sort of filling out those histograms on the 2 sides, that's on the bottom and on the left side, and hopefully it'll eventually fit that sort of fit that's been given to that histogram quite well. But we can make it a bit faster if we just increase the sort of proposal signal that we've got here. So now it's allowed to explore a little bit further out, and it's allowed to explore a little this like weird multimodal region. But you can already kind of see that it's sort of getting stuck in one place. It's definitely sampling all the nodes really well, but even by expanding that proposal signal, it's struggling to really get to every mode at the same time. And this is kind of the issue with a lot of MCMC techniques. It doesn't really, sometimes it can get stuck in a place and can't really go everywhere all at once. If you were to take a different type of sampling technique, something like a nested sampler, you might be able to see pretty easily that it can have these bands and it can converge directly onto these nodes a lot faster. And so while this is really good for this sort of multimodal description, maybe if it was a similar description of posterior description, MCMC would actually be better. This is going to finish in a second, in a fraction of a second compared to MCMC, and it's going to be that. MCMC doesn't really give you that flexibility, but it has still that infinite parallelization, which is really valuable when you start thinking about PTAs as well. So I'll put this in this slide deck online, you can play around with this too, because it is the same amount of fun just to see it wander around. So you can get lots of stuff there. Just jump in here. Cool. And what this basically, how this basically works, so this sort of simple MCMC thing works, is that it's effectively a random walk algorithm that's got selection criteria for taking the next one on. So it's going to create this eigen-direction that it creates through the covariance matrix of the models, so the parameters in the model you're testing, and it will just randomly move one direction or another to a certain point. If that is favored based on this H criteria, which is what we call the acceptance ratio, then it'll move forward and that'll be the next point, and it'll just keep going on in this sort of connected chain. And eventually, over a long period of time, when you get, stick out of myself. How we do this is in Pythagore is by using this thing we call PTA binary function, which is what I just have here. So this is very similar to the one that Daniel was explaining before. The difference here, what we have really is this covariance matrix. And this covariance matrix is also known as the noise covariance matrix, is effectively the covariance of the signals that you have in the data that are described by the noise. And so that gives you the likelihood that we use based on effectively just the covariance of that data with these time extensions. How to get this likelihood function is many pages long, and it's taken a lot of effort, but I do recommend this book up here, which is Steve Taylor's The Dynamics Gravitational Wave Astronomy, and he goes through a very excellent description of how you get this. And also just sort of very overall, a very good overall introduction on how this sort of PTA science. So it'd be great to attend to this workshop. What you get out of that is the beginnings of your posterior distribution. And so that's what this is here. These are what we call chains. And there's a very good way also to trace pulse and chains. They're very good ways to see how your sampling is converging to a result, basically. So over time, on each of these plots, we have like 6 parameters here defining a model. And over time, you can see that they're sort of converging into straight lines. They're not quite there yet. They probably need a little bit longer, these ones. So you can run them for a little bit longer until those chains are fully converged and not really moving around anymore. And eventually, they will give you what we call this posterior distribution. And we will look at that through these corner plot things, which is this. So all this is showing is the constraints on 2 model parameters for a model given some data. And so this is the dispersion version model for a pulsar J929-374 it is right now, Ryan will go over that a bit more tomorrow. But this is saying that we have these one-dimensional probability density distributions describing the parameters of the model. And then in the square here, we can see how those two distributions interact with each other. So if they look sort of like a right angle, then you call it sort of like a general with each other because they can't build a center between them. If they're very circular, only living in one place like this is basically saying that the amplitude of this parameter is this basically the amplitude of this parameter. So they're coming together and converging quite well. So you look at this and you take these as the description of the model parameters. This is pretty good, so we start with things, and we can keep sort of expanding this. This is where we get into what we call hierarchical inference. So the last two we had very well constrained dispersion measure parameters. So what we've added here is now red dots. And it might look a little less constrained. You can see there's sort of like some fuzziness around there, but they're still relatively good. So now we have 4 parameters describing two parts of the model, and so we're going to keep going up. And we can add this on this as well, and we can ask ourselves, does this still look constrained? Is this still useful? Are we still looking at something that's actually going to help describe the model for this pulsar? And we can keep doing this in perpetuity, but let's not do that, because we'll just be here forever. And instead what we can do is we can start seeing ones that aren't constrained. We start looking at parameters that we're putting into this model and seeing that they're basically, there's no piece here. None of this is effectively peaking in any direction. Up here it's going towards the 0 mark. It's not really something you would take into account. It's effectively returning the prior range of the sample. So there's no strong evidence at any point in these prior descriptions, so we wouldn't use this model. But this is really where the beauty of this modeling technique comes in. We can test every possible combination of these models if we want to. The more beauty of it is that it lets us compare directly those evidence values we were talking about before. So we don't have to look through, 6,000 odd models. So for a pulsar timing array, we have 85 pulsars in the MPTA, the mid-cap pulsar timing array, and we've got about 75 models for each of them. That's just the individual models we have on these things. And if I was feeling very mean to myself, I could really bump that up to about 220. But I don't really want to look through 6,375 possible models, and I don't think anyone else does either. So we can just use that evidence we're getting out of the likelihood description before to compare which model is going to be the best. And even if from that point you still need to look into it and still make sure that the most likely models that seem to come out of that make sense, that do actually fit the data well and describe what you think you should be sending. But this is a very good start, and it brings down the 6,000 mark to something like 200. It really makes the workload much easier. And so that's what this is sort of saying here. So this is a description of 1909-16744, one of the pulsars that basically everybody, all the PTAs find. And these are 3 noise models that I determined they need to pulsar. And so we have dispersion measure noise, we've got achromatic red noise, we've got solar wind, the impact of solar wind. And I think this is probably correct. Or when I made this about 4 months ago, I thought this is probably correct. Now I have more data, and now I don't get this anymore. But this was as correct as we had at that point, which is the best description that we can have of this model. So this hierarchical modeling where we're looking at everything all at once and slowly building up to the best description of the data is the safest way to do it. Because I could have added these extra models that might have been in the data at that point, but it would not have suited the data description. It would have just added nothingness, and it would have been very confusing to the other noise processes that we're trying to describe. So yeah, the takeaway with this is with the data you have using this technique, you can be as correct as you can be. And this is a really good description of how this can go very wrong if you don't do it correctly, which is, I just so I know. This is all the pulsars J1747, which we also look at in the pulsar timing array. And so what we have here on these panels, sorry about the pretty terrible margins, but on that top panel we have just the timing residuals as they are observed in the pulsar. And then in the middle, we have the timing residuals once they are removed, the dispersion measure process for this pulsar, leaving only what I thought was achromatic red noise in the pulsar. That was incorrect. So it looks, you can see here, this looks like a very well constrained model for this noise process. And that's just because I told data that it had this in it. That wasn't correct because I didn't use this hierarchical modeling technique. Using the bottom line down here, when we did use proper hierarchical modeling, we were able to see that it looks very different. This strong red curve in that little panel isn't actually existing in the data at the bottom. And some of you may look at this data at the bottom and see those two curves that we have, the chromatic noise and the dispersion measure noise, look a little bit anti-correlated. And that's a very good observation, and we're not totally sure why that is yet. But we're seeing that in more and more, and that's sort of the fun thing about moving noise modeling in this sense. You get to see unexpected things, and you get to really play with the most correct version of the data. But we want to do pulsar timing array science for gravitational waves, or at least I'm really interested in that. And so how does this really, how do gravitational waves come into all this? Well, they're also noise. We're looking at all these signals in the data, they could be anything. One of those signals that is very similar to this fake achromatic noise here is gravitational waves. And so we're trying to find that common signal through all our pulsar timing arrays, which is the signal of gravitational waves. And it kind of makes everything a little bit different and more interesting, a little bit harder, which is a bit more fun. But I think Brian went over this earlier, we're really just looking at this gray stuff technique, the portion here. So LIGO is great, this is going to be really good, but PTA is what matters. And so we're thinking of basically the signals from supermassive black holes emitted at the nanohertz frequency scale, and it's all this incoherent superposition of all of them from the observable universe. And so that gives us what we term as the stochastic gravitational wave background, which lots of people have mentioned already. So I won't go back over explaining exactly what that is, but that's the signal that we think we're going to be seeing. There are other possibilities, but let's just focus on that for now. This really exists in PTAs as two distinct signals, two distinct noise processes. One is what we call a statistically identical noise, and Ryan used this exact same plot the other day. All these curves that we have for these four imaginary pulsars, A, B, C, and D, these have the same statistics that define their noise processes, that define the signals that they can data. But they all look very different. So this is the first thing that we're looking for. We're looking for a statistically identical signature, which is all very different in each data stream. And the second thing we're looking for is what we call the smoking gun of stochastic gravitational wave background detection, which is the correlation, the spatial correlation of these timing ranges and signals through the actual angular separation from the Earth. So if you wanted one pulsar there, one pulsar there, then the angular mate between these arms is where it's the correlation you would expect based on this plot here. It's what we call the Helms-Downs correlation. So where we are, this does kind of change how we do everything in pulsar timing array research. Instead of just looking at the covariance matrix of a single pulsar's data, which is what which is described by diagonal term here, so pulsar 1, pulsar 2, pulsar 3, pulsar 4, that was that covariance matrix we were looking at just before, that C term that I was describing. Now we're looking at the covariance of the entire pulsar timing array. And so where that sort of statistically identical noise is just on that diagonal. We're looking for a statistically identical noise that lives in that diagonal portion. The spatially correlated signal is everywhere outside of that diagonal. This makes it a lot sort of computationally harder, but it also sort of changes the game a little bit. We're not really looking for the same thing anymore. We're looking for a noise process that is identical in all the pulsars, and so it changes the realization of all the noise in all the pulsars at the same time, which makes things more complicated, but also quite a bit more fun to do. Where we are at the moment is we've found this statistically identical noise. It may or may not be gravitational waves, but it's there in the data. And so this is from the mid-cap pulsar timing array. This is the best constraint we have on a statistically identical noise so far. It's a little bit different to other pulsar timing arrays, but it's quite a good constraint. I won't go into too much detail about why that is or why I think that might be. And then in the spatially correlated sense, we have this best constraint that Ryan showed the other day, which is the nanograph result that came out earlier this year. So this is the best published result so far, and it's really a great sort of start to this first foray into this new window into the universe. We can actually start characterizing nanohertz gravitational waves. But we're not quite there yet, and all of this I've been saying is important for a very reason. And it's sort of imaged very well by this plot here. So hierarchical inference might give you, it does give you the best description of your data by being very careful and very slow. When you do that at a PTA, if you do that like a PTA wide setting, rather than just an individual pulsar, then you start to realize these common signals differently in your pulsar timing array. So this is an example from the Parkes pulsar timing array done by Daniel over there. And we have two descriptions of the noise here. One's very basic, which is not using an advanced hierarchical system to define your noise, the Pulsar Timing rate, and the other is advanced, which is using that search for any possible signal and building up the model as you go. They're very different. The amplitudes, the amplitude on the y-axis there, like slightly coincident, basically they're on the edges of each other, and the spectral index is further away from this dashed line. That dashed line is what we expect the spectral index of the gravitational wave background to be. So if the noise in the data that we're seeing is in fact gravitational waves, by not modeling the data appropriately, you are pushing your results further away from the expected value of what we're trying to see. Whether or not that is actually true is very difficult to say because we haven't seen anything yet. But this is sort of the thought we're thinking at the moment, that hierarchical modeling in this sense protects you from potentially misconstructing your statistic when you're trying to find it commonly for all the pulsars. A little message here. We've got about around the corner from the detection, but it's going to happen very, very soon, and everyone's going to be accelerating to it at the same time. It's going to be a really great time for everyone to get involved like this, but hierarchical modeling needs to be the way to go to do this, in my opinion. Because there's going to be a lot of questions about this when it first gets detected, and if we don't have a very, very organized system backing up how we've done this analysis, then we're going to lose a lot of trust in the wider community. And I think this is the safest way it can be done. And I think more and more people are starting to agree about it. In summary, Bayesian inference is your friend. There are tons of tools to let you do this and help you do this. And if you do need any additional help, I can help you do this. I love doing this kind of stuff. I think hierarchical modeling is a safe way forward, and I think everybody else is in that too. The name of the game is finding gravitational waves, and modeling the noise correctly, as we just saw, is very important in doing that correctly or just changing the answer. But there's also so much we don't know, and we really need your help. So hopefully you're very interested and you love noise as much as I do, and you can help me out. Anyway, that's all I have for you. Thanks for listening. Good questions? So MCMC using the tropical states example. So MCMC is the algorithm that was shown there with the acceptance ratio, that is tropical states. And so it does use that. There are many, many different types of MCMC. And the type that's commonly used in pulsar timing arrays is this one called parallel tempered MCMC. And it's basically, it brings down that likelihood surface to be way more even across your entire likelihood surface. And it makes exploration for that surface a lot easier. But that is a tropical states. So that's kind of like the application of that algorithm.